We just saw an example of how slight inaccuracies or imprecisions in measuring our initial conditions could result in widely different forecasts as time goes forward. Now we're going to see what if there's an error in our modeling parameters and how that's going to affect our forecast going forward. So we're again just going to slightly change it. Jumping into the Matlab, the setup is going to be very similar. We'll have the same initial parameters of rho, sigma, and beta. We'll run this for 50 days, let's say, for our value of t. And now I've uncommented the second part where we're going to perturb just the value of rho. So I'm going to again have my baseline performance. It's going to 22 is going to be exactly the same as what we saw 14 was in the last one. Because again, every time we run it with the same exact same initial conditions, exact same parameters, our results will be exactly the same. The differences we're seeing is when we vary the initial conditions a tiny bit or vary the parameters a tiny bit. All right, so here, let me just run up to this point to get my parameters in. I am going to run it again 4 times the baseline, and then each time I'm going to slightly change my value of rho here. So if we see what I'm doing it, I'm multiplying it by 1 plus or minus a very small number, and that's going to be a little bit bigger than my initial rho or a little bit smaller. Right, so just to run this part, we see it's very close to 1 typically, and the rho value is 28. So the rho value I'm going to use on all of these is going to be a little bit more or a little bit less than 28 every time I run it. And notice that sigma and beta I'm leaving alone. Sigma is 10, beta is 8 over 3. So actually the variations or the perturbations I'm putting in for this simulation or the previous one are actually more constrained than in reality they might be, because probably all 3 of our initial conditions would have some uncertainty or imprecision in them. And here our modeling parameters also would probably all have some imprecision. So I'm kind of doing a better case scenario than would be in reality going forward for illustrative purposes. But in reality, sigma, beta, and rho should all have a little bit of uncertainty involved. So I'm going to run it those 4 times, and again, see what happens when my now initial conditions are identical, 1, 0, 1, but the modeling parameters are slightly different on the value of rho. So once again, we see that they started at, in this case, the exact same place, and they are still bundled together as time is moving forward to 6 days into about 10 days of our forecast based on our initial conditions and our model. And now we're going to see visual separations. It's happening actually a little bit before what we saw for the varied initial conditions. And now they're kind of all over the place. Again, the black line is only tracing that baseline, the green ball. The other 3 are for the slightly different values of rho. So their estimates of XYZ are all at this point very different from each other, as we're at 30 days of forecast, 35 days of forecast going into it. And they're really not overlapping, and they're not going to come back together. They're not going to converge like we saw in our linear system. They remain separate as time is going forward, as we're getting to just the 50 days worth of simulation that we're going to run this. So now we've come to the 50 days in our phase space visualization, and we see the estimates of those 4 different runs with very slightly different values of rho, and they are visually all distinct, all different values of x, y, and z. So let's see what happens in the time trace, where we can see a little bit different perspective. Very similar start to what we saw in the first simulation, but now once we hit around 15 days ahead of time, now we have divergence of those 4 simulations, and as time goes forward, they are not repeating, they're not converging back together. They're all making these independent estimates of the time, the temperature, the air pressure, the humidity, whatever it is we're measuring in this simplified version of the model. So we see here one estimate puts the temperature all the way here at like 16, and another estimate for that same day is putting it all the way down here at -14. So very different estimates we're getting based on very, very close values of rho, but slightly different. And we see that the estimates as we move forward in time are getting more and more different for these just 4 examples. Repeating from the 2 simulations we saw, as time went forward, even when we varied very slightly one initial condition or one parameter, the solutions diverged and continued to diverge as time went forward. But this was somewhat conservative of an estimate of the divergence we would see in our real system, because all of our initial conditions should have some uncertainty when we run this, and all of our parameters should as well. So the 3 parameters and the 3 initial conditions would all have a little bit of random each time, because our instruments are only so precise that can measure the initial temperature, humidity, or air pressure, and also the parameters we're using. Again, we only have finite precision that we can use there. And I want to re-emphasize here, the only thing random was the slight addition, slight little extra I was putting on or subtracting from that initial condition on X, or that slight extra I was putting on to rho or taking away from rho. Once we got into the ODE solver, though, everything was purely deterministic. If I run with the exact same initial conditions and parameters multiple times, I will get the exact same results. Those different results I got for the 4 runs were only due to the slight deviation on the initial condition or the parameter. And again, to contrast those previous examples we looked at for the linear systems, that just spring mass damper system, if we had small changes in the initial condition or small changes in that case, all of the parameters we were putting on small deviations, runs were very close together, they all converged, they all went to that same equilibrium point. That was, in this example, not at all the case. They started together relatively and then diverged over time. Our estimates were very different as time moved forward. So a question that'll lead us to the next part of our simulation is, if we have these very large deviations as time goes forward, what use is the model to us? Because we can only have so much precision in how well we know our initial conditions or any of our parameters. What can we do to try and make use of this model? Let's assume the model is perfect. We're still going to have these issues. So one thing we can look at is we can make an estimate of the error or the uncertainty at certain times of our state variables by making a PDF or a probability distribution function of those results. So we're not going to be able to necessarily say what is the value of, let's say, the temperature at 30 days out, but we'll be able to find a range of probable values of the temperature 30 days out. And we're going to be doing this by using a Monte Carlo simulation with our model. So again, we're not going to be trying to get precise values, exact values in our estimates, but more ranges in our estimates.